Today we will talk about dispersion effect. So we already learned the dispersion from the lecture. So we will learn why we're interested in dispersion or how this dispersion plays a role in optics and photonics. So this is the pulse propagation. In communication, we transmit digitized signal 110101. So it's 110101. After the transmission, in optical fiber, the pulse is broadened. The pulse is broadened. Just like what we learned from the class, it has the dispersion effect. It increases the phase increase the phase in the spectrum, so it broadens the signal, the pulse width in time domain. So it has broadened pulse, right, at the chip in the pulse. So in this specific point in here, you need to have a decision circuit. Once you receive the signal, you need to make a decision whether this is the 0 or 1, right? So here it's very obvious, it's 1, 1, 0, and here it's more or less it's 0 and 1. But in this specific point, because there is some kind of signal here, so it's really hard to make a decision whether this is 0 and 1. It will create error, right? So in this case, in the communication, we need to avoid this dispersion. We need to avoid dispersion, right, in order to have decode correctly. Okay, so that's the dispersion. Okay, so we learned previously, this is input pulse, right? So we have envelope, and then this is carrier frequency, right? The carrier frequency, the oscillation. That's what we're talking about, right? 400 nanometer laser, 600 nanometer laser. So this is the carrier frequency. And once you propagate after the fiber, it creates some chips. So it's up chip, right? The frequency increases, right? Frequency increases as a function of time. So it broadens the pulse. But if we have a previously already positively chirped pulse, so we have opposite chirp. If we have an opposite chirp after the fiber, it's the chirp that cancel out. The positively chirped and negative chirp cancel out. So it going back to original pulse. So you can see you can generate a narrower pulse, right? Narrower pulse. And then further propagating in the optical fiber, it generates the additional chirp. So it broadens again. So this picture shows as TZ, right? TZ, it's a Gaussian pulse, the width at the propagation divided by T naught, right? So T naught is the initial pulse width. If we don't have any chirp at the beginning, right? There is no chirp, so the K is the K is the C in our lecture, right? It's from different different paper. So if we don't have initial chirp, the pulse is monotonically increased. So if we have the chirp and the dispersion, they are in the same direction, same actually sign, then the broadening is actually faster than originally no chirp. However, if we have chirp is oppositely, opposite chirped, then the pulse width could be narrower at the beginning, but eventually it's always going up. But you can see actually in this case, the slope is faster than the original one, right? In the end, it will still increase. Okay, so this is the similar figure, right? It is the similar figure, so you can see this is the originally with chirp. This is the original opposite chirp, but that is originally no chirp. But even the C equal to -2 has lowered the pulse width, but eventually it actually broaden faster than originally no chirped case, right? So depending on different chirp, Either they're in the same position with my dispersion, or if you have opposite direction, then you can actually decrease the pulse width. We're going to actually learn this in our lab section. So you will create either positive chirp or negative chirp. Then you can see how pulse broadening and how pulse, narrow, decrease the pulse chirp. Okay, so the pulse compress. Okay, so this is the Gaussian pulse, ZO over LD, right? This is the dispersion length. This is the dispersion length. So usually we characterize the dispersion effect by dispersion length. So if the distance is way less than the dispersion length, so dispersion effect dispersion plays almost no effect. So the pulse is almost no change, right? But if we pass through two dispersion lengths, Z over LD is 2. That means Z is twice of the dispersion length, then pulse broadening, right? Pulse broadening. And if it's 4, pulse further broadening, right? Further broadening. You will reproduce this figure in your lab session, Okay. So let's review what we learned in this chart. Why? We're now very familiar. This is UT, right? This is UT. After the Fourier transform, this becomes U tilde omega. So this is in frequency domain. Then we take propagation, right? So the propagation in time domain is really difficult. So we're going to do it in frequency domain. We need to first do the Fourier transform, then do the propagation, and it happened to be U tilde Z omega, right? We use the Z omega, 0 omega exponential I k naught double prime over 2 omega square Z. So this factor included for the propagation in the spectral domain. After that, you just take the inverse Fourier transform, you get the result in time domain, right? But one thing you will see is that once you multiply by this exponential I k naught double prime over 2 omega square Z, so this is actually pure phase, right? I k naught. So if I take an absolute value square, guess what? This absolute exponential I, something is going to be 1, right? Exponential something, because exponential I theta equals cosine theta plus I sine theta. And take an absolute value square, meaning that it is cosine theta square plus sine theta square, which is 1. So basically, the amplitude does not change in spectrum, right? The amplitude does not change. What changed is the time domain. The pulse is broadened. Now let's look at this example. So the left column is frequency in spectral domain. Right column is in time domain. So this is showing the amplitude, and here we show the phase, right? Okay, so at the beginning, it's the nice Gaussian shape, right? Nice Gaussian shape. Okay. Then we know that this will be our delta nu, right? This will be our delta bandwidth in frequency domain. This will be our delta t, right? That's what we did in the homework to calculate the product of the pulse width in time domain and pulse width in frequency domain. It should be 0.44, right? So these two should lead to 0.44. Okay, so then we have the product. We will have the after propagation of 5,000 kilometer. After propagation of 5,000 kilometer, you can see in the spectrum they have no change. In the spectrum, they have no change, right? In amplitude, but it changes the phase, right? So the color bar indicates the phase, but the envelope, there is no change. Why? Because if I take an absolute square, if I take an absolute square, the amplitude is the same. That's why the amplitude does not change what changed is the phase, this color bar. Right? But in the time domain, it changed the amplitude and also the phase, right? So it changes both the amplitude and phase. It changes both amplitude and phase. Okay, so now let's look at the next one. The left figure is still the same. The right figure shows another example, but now we show both in time domain, time broadening, but now we show the time envelope, but the color shows the frequency, right? Shows the frequency. So it shows that the pulse at different location has different frequency. So that means it's actually at the chip in the time domain, right? It at the chip in time domain. So that now the pulse looks like the previously like those, right? Looks like those or those, right? It has different frequency at different time. It has different frequency at different time. Because of what? Because of this dispersion effect. Because of this term, right? Because of this term. After the Fourier transform, it effectively changed the frequency in time domain. Right? So this is the dispersion effect. Okay. Okay. So this is secant pulse and Gaussian shape. Secant, right? So we learn secant shape and Gaussian shape and also super Gaussian, right? The reason why we learn that is different laser actually output different shape. It's not exactly the same as either Gaussian or secant. So sometimes we use secant, sometimes we use Gaussian, depending on the real experimental results, right? So that again, what is four-wave half maximum? That means if it's in time, right? So this is the this should be power, actually. So power we'll look at half, 0.5. So the four-wave half maximum, this is roughly about 1 picosecond, right? So 1 picosecond is the four-wave half maximum of this pulse. They are almost the same, right? For the secant shape and Gaussian shape. Okay, so that's the attenuation and dispersion, right? So this is mainly attenuation. This is the optical fiber, the loss, right? The loss. The left one, this is Rayleigh scattering. That's due to the scattered from different atoms, scattered loss, right? Scattered loss. And on the right shoulder, it's infrared absorption. It's due to the infrared absorption. So those are fundamental limits. In between, there's OH actual absorption. So it's due to the OH absorption. And here is the minimum. So that's the silica glass. Silica glass. So silica glass has the minimum loss at 1550 nanometer. At 1550 nanometer. That's why most of the optical communication, they transmit at 1550 nanometer. But now, because those are so low, they actually use different wavelengths. You use wavelength division multiplexing, so you can transmit several wavelengths because they don't interfere with each other. You can demultiplexing easily separate out different channel. But mostly the communication occur at 1550 nanometer. Okay, so I want to actually show the dispersion using the published data. So it's in the literature. People have done a lot of research in the 1980s. So it's almost 30 years ago, right? Oh, wow. It's almost 40 years ago, sorry. So it's 40 years ago, 1982, right? It's 40 years ago. At that time, dispersion is the main actual research topic. But nowadays, because people already know dispersion effect very well, so this dispersion is not the research topic anymore. So I actually dig through those papers back in 1980 something. So let's take a look what people have done at that time on dispersion effect. So this so this paper talks about this optical total output waveform in time domain. So this is in time domain, but at different time, slice of time, they put the Fourier transform. So they pick up different slice of time. They plot in the spectrum domain. You can see that different slices of time has different frequency, right? So this is a chirped pulse. This is a chirped pulse because different slice of time corresponding to different central frequency, right? Different frequency. So it's a chirped pulse. So once we have chirped pulse passing through a fiber, C is greater than 0, beta 2 is negative. So they oppositely interact with each other. That's why the pulse width is going down, right? The pulse width is going down. So it has a narrower pulse. The pulse is compressed. You can see this is 30 kilometer and 50 kilometer, 80 kilometer, 104 kilometer. The pulse width is narrowing, right? But of course, it becomes a lot of noisy signal, very noisy signal, right? Noisy signal. But the dispersion effect does narrow, compress this pulse. Okay, so this is the simulation. The curve is the simulation. The dot is the experimental result. The dot is experimental result. You can see it does compress in some degree from 180 picosecond to 150 or 60 picosecond. It does compress, right? And this is additional simulation data. You can see it can compress in different cases by 400 to 220. So it's compressed almost by half. Compressed almost by half. Okay, so this is another example. You can see if there is no dispersion, the pulse width is the 1600 picosecond. But if we add the dispersion, right? If we add the dispersion, the pulse width is, this is experimental result, this is simulation results, right? I mean, you can do that too, right? So you can use the code we assigned as the homework problem. You can actually reproduce this data, this curve, right? It's going down and going up, right? Going down, going up. Because what? They cancel the dispersion, right? They cancel the dispersion. Okay, so here's another example. This is a new another paper published in 1985. So we will focus on the pulse propagation in the optical fiber. So this is the pulse narrowing, right? Pulse narrowing. Okay, so you can see this is the pulse at the pulse width, right? Pulse width. We look at 4-wave half maxima, right? Half of this maxima. What's the width? This original width is 26 picosecond. And now it is the 13 picosecond. So it's way narrow. It's almost half, right? It's almost half. So this is measured. So those data, the solid data is the measured. And then the curve is the fitting curve. And then estimate simulation is from this dashed, right? And use open circle, right? Okay, and you can also do the Fourier transform, look at in the spectrum domain, right? So this is experimental results, of course, right? Experimental result. You can see it's 85 gigahertz. Using what we learned in the homework, right? So delta T and delta nu. So delta nu is the bandwidth in frequency domain, right? So it's not angular frequency, it's the in frequency. So delta T times delta nu is 16 picosecond times 85 gigahertz. You end up with 1.1, right? End up 1.1. So delta T and delta nu is greater than 0.44. We learned from the homework is that a Gaussian, very nice Gaussian signal, the product is 0.44. So in those two, that means if it's 1.1 is greater than 0.44, that means it is not a Gaussian, transform limited pulse. So meaning that it has chirp in it. If without chirp, it is 0.44. 1.1, that means it has chirp in it, right? It has chirp in it. So it is it has the chirp in this pulse. So previous case, we always believe that the dispersion is bad, right? Dispersion is bad, because it broadens the pulse, because it makes the pulse not it's hard to detect the pulse, because pulse width is broadened. It goes to the next bit, right? As I explained in the first figure. But sometimes the dispersion can be good, right? So this is called chirped pulse amplification. Chirped pulse amplification. Let's look at this. Is the short pulse oscillator. Is the laser. So initial short pulse, and then it adds the dispersion. The way it adds, it's called grating, right? We're not focusing on the grating, but you can just think of a fiber, a section of fiber. So it will broaden the pulse. So you can see after that, it will go back. So let me actually talk about this grating. So once we hit here, it separates out, the grating will separate out into different wavelengths going to different direction. And here, different wavelengths going to different direction. It has a mirror, because different wavelengths passing through different optical paths. So it creates different phase or delay time for different frequency. That's why it's actually at the chirp in this pulse. So it broadens the pulse. Initially, it's very narrow, but now it's very long. And also, it has chirp in it. It has different frequency. This work does not use fiber, because fiber, the dispersion effect is relatively low, right? Relatively low. This device can add way higher dispersion than optical fiber. Okay. So we have the very broad pulse, and then it passing through optical amplifier, passing through the optical amplifier. So this very wide pulse being amplified, right? So high energy pulse after amplification. Then you passing through a dispersion with an opposite sign, right? You pass through an opposite dispersion material. So at the end, we actually, because it takes the opposite effect of the original broadening. So it narrow or compress the pulse. So the pulse width is going to be the same. Pulse width is going to be the same, because the dispersion effect, they just do the opposite effect, right? But now the pulse energy is way higher than the original energy, right? This pulse is way higher than original energy. So you need to first stretch out the pulse, you broaden the pulse, get the amplification, and then you actually you narrow, compress the pulse, become very high power. You may ask, why bother? Why don't I have an optical amplifier directly amplify this original pulse? Direct amplification is very hard, because you have very narrow pulse. Amplify in narrow pulse is really hard. And also, if the peak power is very high, it might damage the optical amplifier. But in this case, I have very wide pulse, and the peak power, it may not be very, this is actually, it's a little bit exaggerated, right? So in the real case, this power is real high, right? So in a very broad pulse, the amplitude is a little bit high, but not as high as this narrow pulse, right? So if you have you broaden it, amplify it, and then narrow it, it becomes very high pulse. It has very broad application in this case, right? So due to their contribution, the physicists win the Nobel Prize in physics in 2018. So this technology won the Nobel Prize in 2018. So that's how the chirped dispersion can play a positive role in the optics and photonics.